Second question. How does the metallurgical treatment of the palladium influence this?
All of our samples were cast. I think most of the commercial samples of wires that you buy are extruded. In one casting that did not work, this blank electrode that I told you that does not work, that particular one came out of the casting in quite bad shape, and they milled it, they machined it, and that one never worked either. So there is a metallurgical, we think there is a metallurgical problem here. Certainly cast electrodes have a better performance ratio than extruded. So I do not know enough about that problem yet. We've sent some of the samples back to Johnson and Matthey for surface and bulk analysis.
Way back. And yes, and please speak up so we can all hear.
Okay. We've heard that the reads in your experiment on the palladium electrode have some role in results that you see. Could you elaborate on that? Do you need palladium reads on the palladium electrode, or
we have simply always used, in order to omit any confusion about junction potentials and other chemical effects that may take place, have simply always used 100 micron, I think it's 150 or 100 micron palladium wire that has been spot welded to the top of the palladium rod. That's always been our connection. I understand that there has been some extremely high junction or capacitances measured between beta palladium hydride and things like copper, for instance. In fact, they exceed those of barium tantalate in some cases. So there is an implication that this is a much higher dielectric constant in beta palladium hydride, which can be seen. So I don't know. We need to look at that, but we've always just used the palladium. It seems a lot less ambiguous.
I believe you made a comment that it's necessary to use palladium rods rather than, say, palladium foil.
Well, no, the reason we went to rods was to have a convenient method for maximizing the volume to surface area ratio, so we could unambiguously say that this process is a function of the volume of the metal. In other words, it takes place inside the metal. We have used sheets. Sheets, indeed, will be a method for building a conventional or a device, for instance, for heat production. But you can certainly use any geometry you want. The important parameter is you have volume. Well, no, the important parameter is that you have volume, period, so that you have volume to carry on the reaction. We just wanted to show that the effects we were seeing were not due to a surface chemical reaction. We wanted to show that it was a function of the volume. The important parameter is volume.
But if you reversed it and used and didn't control surface area, just controlled volume, you'd expect the same result.
I don't follow that.
You said that only volume was important.
No, we simply wanted to show that the heat, the excess heat we were seeing, was a function of the volume of the electrode and not the surface area. I mean, as you make the rod larger and larger, if you make the rod larger and larger, we have a direct relationship between the heat involved and the volume of the electrode. The area increases much slower, at a much slower rate, and so we did not. So it's.
Well, you can show that by maximizing the volume to surface area ratio, or
well, that's what you do.
You can show that it's independent.
Yeah, I mean, a rod is simply the most convenient way of doing that, because you have. I mean, you could go to spheres. Spheres would be ideal, but that's very difficult to make. So rods give you a very high volume to area ratio, so you get a lot of the effect. Number one, and it brings it away from the surface area dependence.
In the experiment which detected helium, what was the idea?
Can you please stand up and speak loudly so we can all hear?
In the experiment which detected helium, what was the ratio of helium 3 to 4?
Helium 3 to 4? We did not measure. We have not measured helium 3. I think its mass is too close to. Is it? I don't remember if it's tritium or the H3 plus that it's so close to. Both which are present in the system.
I understand that D2O can have tritium, and that's an impurity quite often.
That's correct.
Is there any tritium in your original?
Yeah, have a copy of the paper with me, but it's in the paper, and that's the experiment which I showed here started out at 18 disintegrations per minute and ended up at 100 and I just don't remember the figure. It was something 225, something like that per minute. It's in the paper, and it goes along a curve which was predicted by the differential equation which we solved for the accumulation.
Do you think the peculiar properties of palladium are essential to this experiment?
No, I think any number of metals which show high, or alloys which show high hydrogen permeability may be of that crystal structure anyway, could give the same result. We have not tried any other metals yet, but we certainly are going to try. Titanium, for instance. Titanium absorbs many times more hydrogen at high temperature than does palladium.
Do you have any comparison between the amount of helium-4 that was measured in the earlier experiment and the amount of excess heat?
Again, that prediction is in the Simons-Walling paper. I'm sending copies of that down to Rulon in the next few days, so he will have that and make it available to you. But they made a very close prediction as to the excess heat generated.
Have you tried to pre-saturate your palladium with deuterium to change the initiation time of the reaction?
No, that's something that needs to be done. One thing we want to start doing is trying to load them at higher temperatures, say at 80 or 90 degrees, and then cooling them down for the experiments. But there's a lot of ways probably to do that, and that needs to be done.
What evidence do you have that these lattice sites are multiply occupied?
We have no direct evidence that they're multiply occupied.
Calculation.
We are doing those now. Jack Simons is doing some ab initio calculations on those now.
Can you describe how long after the initiation of the experiment you first see excess heat, and then subsequently how long does it take the excess heat to reach equilibrium?
All of the experiments are at equilibrium, well, up to a 4 millimeter rod are at equilibrium by 250 hours after we start. There is a slow rise, well, there's the expected rise in temperature that you would expect from just Joule heating in the cell over about several hours after you start the experiment. And then for an electrode that takes, say, 3 weeks to charge up, you will see not too much of a change over the next week and a half, and then in the last week you will start to see the temperature rise from that up to the 6.5 degrees that you saw here. So that temperature cycle takes about a week. We usually wait about 5 times the diffusional relaxation time before we think the thing is at total equilibrium.
Can you describe a little more about the experiment that failed and what you observed when that was concluded and what you did to analyze the results and what you think?
Which experiment is that now? The
one that vaporized or self-destructed?
It was a bit of a mess, to say the least, but that had been running for several months, and we decided to start doing the thermochemistry, so we wanted to turn the cell off. So we turned it off too quickly, and several hours later that accident happened, and it vaporized 90% of the cube and the bottom of the vessel and some of the surrounding materials and equipment in the hood.